The one I want you to introduce and the one that I want you to learn and the one that you will have to do an exercise, your last lab will be doing one exercise with these systems, is behavior trees. Okay, the difference or the main difference between behavior trees and all the rest, hierarchical state machines, graphs at Petri nets, all of this, is that behavior trees, as its name says, uses trees, while all the other uses graphs. When we use graphs, we start having lots of loops, lots of dependencies that make things not easy to maintain, very easy to make mistakes, let's say, okay? However, when we use trees, everything is much simple, okay? For instance, here, okay, in this case, the tree is pretty simple, no, because it's just detecting an object, open the gripper, move over the object, approaching to the object or grasping them, closing the gripper, and we have grasped something. But here, if we start adding some possible failures, some possible things that has to be repeated, etc., here we will start having loops and strange things that can make this pretty simple state machine, finite state machine, not so easy to follow and to maintain. If we use behavior trees, we will see now with some examples that this can be much simplified. The nice thing or the strange thing of the behavior trees is that they do not appear for robotics. The people that invents behavior trees was the game industry. Behavior trees was an easy way to provide intelligence to the non-playable characters, you know, the NPCs that appear in the games. Then they just program NPCs using behavior trees. They have some behaviors, I don't know, the typical soldier that just move up and down to a corridor, and if you are in the line of sight of it, then it will say alarm, alarm, and start shooting you, whatever, okay? This is games that probably we have all played, okay? Then to do these things, they usually have scripts. Lua, for instance, was very popular in video games to program these kind of things. They also use state machines. But nowadays, the biggest engines, game engines, Unity, Unreal, etc., provide behavior trees. And behavior trees become very popular because of that, because it's much simple to deal with all this complexity that we have. Then let's explain a little bit how a behavior tree works, okay? Because they are trees, they have a single root node, okay? Here it was the sequence root, but doesn't matter if it's a sequence or if it's something else, but they have a single root node always. And then they have the internal nodes that are the ones that control the flow, okay? What it's going to be executed, decide what it's going to be executed, but not the execution itself, and the leaf nodes that contain the nodes that are going to be executed, okay? It means that whenever we have a skill in our robot, for instance, moving from one point to another, detecting if there is a blue ball in front of the robot, things like that, they will be leaves. All these primitives that our robot is able to do will be leaves nodes. And all the internal nodes will be things that are from the behavior tree, depending which behavior tree engine you use, you will have more or less, or they will be named one way or the other way, but this will be provided by the behavior tree engine. We only need to deal with the leaves. And the idea here is that we have like two types of behavior trees. The ones that has no memory, that are the originals and very well suited for robotics also, and the ones that have memory that are a little bit simple to understand, and okay, we will play a little bit with both of them. The idea is that every time that the behavior tree receives a tick is like a signal, okay? You have to think that this is task planning, okay? It's not control. Here we do not try to send a signal to our robot 10 times per second or 20 times per second or 100 times per second. Here we just change tasks. If we do it every 1 second or every 2 seconds, it's more than enough, okay? We don't need to be as fast. Then we send one of these tick messages, for instance, every second, and then when we send this tick, what the behavior tree engine does is, starting from the root, it goes from left to right in depth first traversal, then it tries to go from the very end to the left branch, then to the right, until it reaches the very end of the most right branch, and checks which which leaf it has to execute, or if more than one leaf has to be executed, okay? When the control flow receives a tick, it just says, okay, which of its childs has to be executed, and when an execution node receives a tick, it can or either execute something, or if it's already executing something, say, hey, I'm running, okay, just wait. And this is what we will see now. Okay, then, let's start for the leaf nodes, okay? The leaf nodes will be in the, you remember, when normally in computer science, when we talk about trees, we always have upside down trees, okay? This is the root, these are the leaves, okay? You have to imagine a tree upside down. Okay, then, let's start for the leaves, that is where we have most of the work, because we need to define which primitives we have in our vehicle and which checks conditions, that are also things that we will execute in our vehicle, we have. The difference between a primitive action and a check condition is that a primitive action is something that requires time. For instance, moving from A to B requires time. Okay, it's something that in 1 second I will not accomplish. However, checking for a condition is this, if your battery over 50%, this is something that is immediate, okay? Then this is why we differentiate between these more elliptical shapes and these square shapes, okay? But they are all things that in the end are translated into reading a topic or sending an action in your ROS system, okay? One will take for a while, and then we need to keep track, okay? We are executing this, then we have to wait, no, we have reached the end, yes, no, it has failed, it has succeeded, what happens? And the others are immediate. But doesn't matter which one we have, if it's an action or if a condition, they always return one of these 3 states. They return success if the condition that you want to check is true, or if the action that you are trying to execute has been successfully completed. They return failure if the condition that you are checking is not true, or if the action that you are trying to execute has finished in a not successful state. And running, this is only for the action nodes, if the action that you are trying to execute is still running, okay? Normally, condition blocks or condition leaves never return running, okay? This is the idea. Then these are our trees, our leaves, sorry, and they are pretty simple, okay? You only need to do this small interface between the behavior tree action and your real action, your motion planner, for instance, or your grasp system, in order that when someone activates you, when you receive the tick, if you are stopped, then you start and send a running action, and then you keep executing. If while you are executing, someone asks you, you keep sending this running, and the moment that you stop, you record if you have a stop in a successful state or in a failure state, and when someone asks you, when you receive again the tick, you tell, I have succeeded or I have failed. Okay, this is the leaves. And now let's see the control flow nodes. These are the ones provided directly by behavior trees. And the good thing here is that we mostly have only 3 control flow nodes, okay? It's not exactly true, because then we have these decorators, okay? These decorators should be here, this drawing, but okay, it's fine. And from decorators you can have as many as you want. But the main control blocks are only 3. This makes things pretty simple. Which are, we have a sequence. A sequence means that if I have a, maybe it's even easier if I draw it. Okay, if I have a sequence block, and here I have, I don't know, 1 condition, 1 action, and 1 action, the moment that this one receives a tick, the first thing it will do is send this tick to its first child, and then check this condition. If the condition is true, it will return success, and then the sequence will send the tick to the second child. If this action finalizes with a success, it will return the success to the sequence, and it will send the tick to the third child. Whenever this child returns success, the full sequence will return a success to whatever it has on top of it. Okay? However, if any of the childs, the first, second, or the third, whatever, returns a failure, the whole sequence is abort. Then imagine that the first condition it's success, but the first action it's fails, returns a failure. Then this will never be executed, the third child will never be executed, and the whole sequence will return to whatever it has on top of it, a failure. If there is a running, if this returns a running, then the sequence will return a running, and this will also move up. This is the sequence. This is the most used one. The second one is the fallback or selector. This depends a little bit on the behavior engine you use. You will find the word fallback maybe more popular, or the word selector, but they work exactly the same way. And it's like not the opposite of the sequence, but almost, okay? Imagine that we have a fallback. I think they draw it more or less like something like that. We have a fallback here, fallback, and again, this fallback has 3 childs. This is the opposite almost, okay? You try to execute the first child. If the first child returns a success, the whole fallback returns a success, and the other childs are never executed, okay? However, if the first child returns a failure, instead of returning a failure, it just executes the second child. And if the second child executes again a failure, it executes the third child. If all the childs return a failure, then yes, then the fallback returns a failure. But if any of the childs return a success, the fallback returns a success. Okay? With that, you can maybe probably already see that we can do if-then-else structures, okay, with something like that. And then finally, we have the parallel that is not so popular, but it's very useful in some situations. Here, the idea is that we execute currently all the childs. Okay, imagine that we don't have this. That now I don't remember the symbol for parallel. But parallel, let's say here we have 2 childs, and the 2 childs are executed simultaneously. And for parallels, yes, they have like a configuration that you have to say when they return success and when they return failure, and which is the behavior. Then, although we have a single parallel block here, in fact, there is more than one parallel blocks. It can be that you execute something in parallel, and the sooner that one returns success, you return success. The sooner that one returns failure, you return failure. That you force the two childs to complete its execution, and then you return an end of the output or an OR of the output, etc. Then there are more than one parallel, okay? But the idea is this one, that all the blocks that hang from the parallel, all the childs of this parallel are executed in parallel. And of course, a control flow do not have to have only leaves as childs. It can have other control flows, okay? Then you can do quite complex structure combining different control flows. Finally, there are the decorators. Decorators are useful for some things. For instance, here I want to check something, but checking that, it just takes half a second, and it returns me success or failure. But if it returns a failure, I don't want to return directly a failure here in this sequence. I want to keep trying up to 10 times. And if after 10 times it still is a failure, then yes. But during 10 times, no. To do that, or I need to put like a fallback with 10 times the same behavior, that is not very nice, or I just can put this simple decorator that says repeat 10. And then it generates that 10 times, or until a success happens. Okay? I can have another decorator that just inverts. If something returns a failure, it returns a success. If something returns a success, it returns a failure. An inverter. It's very useful, the inverter, the inverser. You will see it in some of the exercises that we will do, etc. But this is all. This is the whole theory to explain what a behavior tree is basically that, okay, in a nutshell. A very simple example, okay, this is a state machine we have a door that the current state, well, we are in the start, and if we check the door is closed or not, and according to that, we decide that the door is closed, we then execute the action open door, this may success or may fail, and then we are in a state that the door is locked. In this state, we can unlock the door or return a failure, how we can represent that using behavior trees. Okay, no, I don't have it here. I have to do it in the Blackboard. Okay, imagine, okay, we have a door closed, no? Then we need to decide what we are going to do. Probably this is going to be a sequence, no? Because here we have the open door. Well, first we have a check door. If we need to check, let's assume that this is a sequence, okay? First we will check the door. Well, in fact, it's not a sequence, it's a fallback, sorry. It's a fallback, yeah. Fallback. We will check if the door is closed, if the door is open. If the door is open, it automatically returns that the door is open. If not, what we are going to do is try to open the door. This is an action, then open door. If this succeeds, we are done. If this fails, then what we can do is try to unlock the door. Unlock. Maybe here it will be better to do something like a sequence in which we first try to unlock, and then if we have been able to unlock, only if we are able to unlock, we then open. Okay, something like that, for instance. I don't know. Something like that will work, okay? We check if the door is open. If it's open, we are done. If not, we try to open the door. If we are able to open the door, we are done. If not, we go to this sequence in which we first unlock. If this fails, everything fails, because this fails, and because all of them have failed, the fallback also fails. If this succeeds, then, because it's a sequence, we execute the other one, that is open the door. If this fails, then everything will fail again. Okay? Something like that will work. And you see, we don't have this graph structure. It's always a tree. And then it will be very easy that every time that I want to use that, I just take from this fallback and I copy to another place, or all this can be transformed into a single leaf and put it in my tree, wherever I want. This is a slightly more complex behavior, but it's similar. A robot has to walk to a door and cross it, not only open it, but cross it, and the door is closed. If the door is closed, we can try to open. If not, we can try to unlock, like we did here. And if we cannot open, not unlock, we can just smash it. Okay, and then what we have is we have these actions. Okay, these are the actions that our robot has: walk to the door, cross the door, unlock the door, close the door, open the door, smash the door, and we can check if the door is open or not. How we can do that? For instance, using this, no? Here we have a sequence that first we move towards the door. If we arrive to the door, you see, we have exactly this fallback here, no? Check if the door is open. If the door is open, cross it. If not, in a sequence, unlock the door and open the door. Okay, it's missing the smash the door because I'm a nice guy, I never smash doors. But okay, it's the same, you see, no? And whenever we have completed that, when our sequence finalizes, we can just cross the door. And as I told you, this part here is a subtree. It's this subtree, the one that we have done just before. Then we can just reuse that. It will look something like that. Okay, there is a famous editor that is called Groot. I think it's called Groot. That is an editor to write behavior trees. It's tied to a specific behavior tree engine that is called Behavior Tree C++. That is for ROS 1 and ROS 2. In previous years, we used to use something else that is called PyTrees. That is another system, another library that allows you to execute behavior trees in Python. However, I used the version in ROS 1, the version in ROS 2, I've never used it. And because this year we try to compact a little bit more the classes, I will not make you any exercise with PyTrees, but just drawing behavior trees at hand. I think it's a very good exercise for you. If we try to represent this behavior tree, okay, to be honest, this behavior tree using a state machine, we have something like that, okay? Again, it's not super complex. It's easy to follow. Maybe it's easier to follow than the behavior tree if you have no idea about what a behavior tree is, because this is pretty clear. But it's very easy to make a mistake here, okay? And if you want to add or replace something, it's more challenging. And this is a very simple thing. I mean, whenever we start doing complex behaviors, this grows exponentially, okay? Then, just one last thing. As I told you, behavior trees can be of two types. Can be with memory, then they are non-reactives, and with reactive behavior trees. Basically, the ones that has memory, when a node returns running, you are executing a behavior tree and you end up in a node that returns running, you stay there. And the next time the root receives a tick, you don't start for the beginning of the tree. You go directly to this node and say, are you still running? And if it's still running, then you just wait until it says success or failure. Remember, leaves can only return running, success or failure. Then the ones that has memory, they just keep asking and asking the nodes that are running until these nodes are success or failure. However, reactive trees, no. Reactive trees always start for the beginning. It's a little bit crazy to design a reactive behavior tree, okay? Because it's not the natural way to think for us. They are very useful, they are very powerful, but it's not the natural way that we used to, at least me, try to think the things. Okay, for instance, imagine, consider that an industrial manipulator in a production line must pick and place an object, typical pick and place, super simple. After grasping an object, we cannot guarantee that this object is not going to drop, okay? That it will not to slip from the gripper. Therefore, while we move, we should be always checking. If the object is no longer grasped, then we can immediately react and recover the object. How we are going to implement that using a reactive behavior tree? With something like that, okay? We have a sequence. Normally what we will say is grasp object, move object, place object. This is our typical industrial robotics lab, no? Okay, I have a BAL3 program or whatever program I'm using, no language I'm using. I just ask the robot to grasp it, to move to a position, move line, close grip, grasp, then move the object, move line, move join, move line, no? Move to the correct position, and then place the object, no? Move line, open, move line, whatever, no? This is the typical procedure that we are going to do. But if we want to do that, we just need to add this. Is the object grasped? I don't know, maybe asking you know that some of the industrial robots detect if they have something holding or the vacuum that they do to hold something is still working or not, etc. Then if we just do this fallback here, because every time what we will do is the object grasped? No. Then grasp the object, running. Is the object grasped? No. Then grasp the object, running. And whenever this one has grasped the object, it will say, is the object grasped? Yes. Then move the object, running. Is the object grasped? Yes. Move the object, running. Is the object grasped? No, it has dropped. Okay, then grasp the object. You will see, because it's going to execute this tree from the beginning every time, every second or every 2 seconds, wherever you program. We have to do nothing. We only need to program this extra, is the object grasped? And that's all. Okay? Our program is automatically reactive. Okay? Yeah, there is this very last concept that maybe I have time to explain in 2 minutes. That the problem with behavior trees, state machines, all these formalisms is how we pass information between primitives, okay? The idea that they end up using in behavior trees is very simple. It's using a blackboard. Blackboard is like a centralized database in which all primitives, all behaviors, all the leaves can store information in there and read information from this blackboard, okay? And the idea is that this is a centralized data storage. It's completely decoupled from the nodes. Then the nodes can access it and write it, but of course, in your task, if you have a node that reads something from the blackboard, you first need a node that writes something in the blackboard. There is this coupling, but it's not a lot of coupling. Then it's easy to port things from one state to the other, and it can be used for things like the state management. Okay, if you want to keep track of some elements, for instance, how many times I've grasped an object and placed it in the correct place. Then it's information that, because you will be executing the same behavior tree all the time, to know how many times you have executed this behavior tree, you need to store a bar in the blackboard and then provide flexibility. Okay, this is, okay, imagine the detect objects, writes in the blackboard the position of the object, the X and the Y, and then when the move object is executed, the first thing it does is just read in the blackboard where is the position. This allows a lot of decoupling, okay? We want to implement a non-reactive behavior tree to accomplish the following task, okay? A robot explores an unknown area while collecting all objects specified that it encounters. This task is almost the same task, that you will have to implement in the last lab. Remember, today I think you have the 4th session for the motion planning lab. The idea is that more or less everything should be working. You still have 1 more week to present your final report, but today you should be able to do a demo of whatever you have right now to Marta, okay, with a real robot. And if it's not working well with the real robot, at least with a simulator, okay? But you have to show she's something. It's like this intermediate evaluation that we are doing. If you are super late and today you can only show it in the simulator, maybe you can ask she if you can show it next week with the real robot. For the last week, I will present an exercise today that is very similar to this one. And the nice thing is that you will have to implement both using behavior trees and using automated planning. That is what we will do in the second part of the class. The same exercise have to be implemented with the 2 different methods. It's not exactly the same exercise, you will see why, but this is the idea. Then I will present it in class. You will have 2 hours with Marta in the office, in the lab. If you have any question, any doubt, anything, to ask she. For this lab, you don't need to use a robot, okay? And then you have just to deliver it. That's all. Okay, but it's something that you can do at home, mostly. Okay, then let's see this example that, as I told you, is pretty similar, although I want you to implement it slightly different for the lab. I will talk about that later. The idea here is to implement this a robot exploring an unknown area while collecting all the objects of a specific type that it finds, that it encounters. And to do that, we rely on the following behaviors. We have an exploration algorithm that just tells us at which is the next best viewpoint that we should move. Remember when we do the exploration topic, in which basically these algorithms, what they do, they propose the next best viewpoint in order to be sure that you have explored the full area. Okay, then we will have one of these ones. We will have a motion planner. You know perfectly what a motion planner is. It allows you to move, to generate a path, not to move, to plan a path from one point to another. A path follower, if you already have a path, something that allows you to follow the path. An object detector, if you are moving, then you can, using your camera or whatever, you can detect if there is some object or not. And an object grasping, something similar of what you implement with Patrick. Maybe you will find small differences if you download the slides last week, because yesterday when I was checking for this session, I just replaced a couple of slides. It's only a couple of them, but I mean, if you want to download it again, you will have exactly what I show you here. Okay, these are the same behaviors as explained to you, but here I put when they return running, when they return success, and when they return failure. It's more or less logic, okay? For exploration, that maybe is the more strange one. Running while they are computing the next best viewpoint, okay? It takes some time to do that. It's not something that can, the moment that you enable this behavior, it cannot give you an answer in milliseconds. It has to take some time. Then probably it will take 1 tick or 2 ticks returning running, and after 1 or 2 seconds, it will return you the next best viewpoint that you have to visit. In this moment, it will return success, and it will store in the blackboard this next viewpoint. And it returns failure only if there are no more points to explore, okay? Remember when we were doing the exploration, I don't know, frontier-based exploration, for instance, whenever we have no frontiers, or all the frontiers are so small that it's not worth going there, then in this moment, it will return failure. It's over, okay? Motion planner, basically while it computes the path, and success when the path is found, failure if there is no path, path follow, running while it's following the path, success if the path is complete, failure, we will assume that it never returns failure, okay? But it should be if something unexpected happens, okay? In the exercise, I've not planned what happens if this one returns a failure. I assume that it always works to make the exercise a little bit simple. Behavior trees grow a lot, you will see, okay? Then this is a small simplification of how we can implement that. In the lab, I ask you to go a little bit deeper. Not a lot deeper, but a little bit deeper. Detect object, again, running while there is no objects of interest in the camera stream. Success if an object passes in front of the camera, and also it stores the position of the object in the blackboard. And failure is again, I will not assume that this node can return a failure, but we should be able to implement here some extra logics in order if this one fails. And then we have a couple of extra behaviors. One is separate from obstacle. Probably you have already experimented that when you try to plan, if for any reason the old plan that you have executed led the robot very, very close to an object, it may happen that when you try to plan from this position to another position, it always fails, it always fails, it always fails. And it's basically because almost all the path that you generate from your current position pass so close to the obstacle that you have just in front that all of them are invalid. This is something very common and happens a lot. The easiest way to solve that is just to execute a very stupid behavior that detects this situation and moves the robot a little bit away from the closest obstacle, and then runs the motion planning again. Okay, then we assume that we already have a behavior to do that, and then if we detect that our motion planning is failing, we just will run this node and assume that everything will work fine. And again, a grasp object behavior that assumes that we are able to grasp an object. In addition, we will have support actions, okay? The behaviors or actions, you can find both names, to bright and red and set bars in the blackboard. And let's start, okay? Let's start by the beginning. We don't want to implement the whole exercise altogether. Let's do it in the blackboard maybe. I think I have here something. Okay, let's start. What we want to start doing is just do basic exploration, okay? We don't want to check for objects and grasp them. We just want something that is able to explore the environment, and once the best viewpoint is computed, plan a path and follow it. That's all. This very, very, very simple thing. And then, whenever we have this done, we will add a word. A word is a word that they sound similar. A word is a word that people from behavior trees used to use. It's like an if, okay? If this happens, do this. If this do not happen, don't execute all these branches, something like that, okay? Then, basically, we will always start in the root. All our systems start in the root. And then, basically, what we are going to do here, you can do the behavior trees from up to down or from left to right, okay? Doesn't matter. Here, because of the shape of my blackboard, I will do it from left to right. Okay, then here what we have to do is to execute the exploration node, okay, the explore node. But explore this node. If this works fine, we will imagine that this sets in the blackboard the variable next viewpoint. Then imagine that we have our blackboard here, then we will assume that this explore node will put here the next viewpoint bar, will define this variable in the blackboard. And then we will have a motion planner that just reads this position from the blackboard and sets a path in the blackboard. And then we have path following, something like that, no? A motion planner, where it is? A path follow. We have a path follow a behavior again that reads the path from the blackboard and follows this path. And therefore, here we can just put a sequence. Then the root goes to sequence, and the sequence executes this tree. Okay, this is the most simple thing that we can imagine. But what happens? That things may fail, and then we have to make a little bit of logic here for the things that may fail. For instance, the first thing that we should check is that what happens if this one fails? Okay, right now, if this one fails, the whole sequence fails. Okay, maybe we have already finished, then it's maybe not good, just the whole sequence fail. Then one thing that we can do here is instead of executing the Explorer directly, put here a fallback, okay? And then execute here the exploration, and then do two things. The sequence that will allow us that will allow us to do two things. I think I will show you directly the solution in the Blackboard because in the slides because it's occupying a lot. The first thing is to set in the Blackboard exploration done. We set this in the exploration done, and then we can return a failure here. Okay, always failure. Always fail. Then what this allows us to do is that if the exploration goes fine, if it just sets the next viewpoint here, this returns success, the fallback returns success, and then we execute the motion planner. However, if this fails, and only if this fails, we set in the Blackboard exploration done. Why we want this? Because the nice thing will be that just at the beginning of everything, we have here a word, that is what the second point tells us, that basically says, check Blackboard, exploration done. Exploration done. What we get from that now, imagine, I take the root, I check that. If this, of course, I should have to, before this sequence, I should have to reinitialize this information in the Blackboard. But as I told you, now it's a simplification. Then, if I check here and I detect that the exploration done exploration not done. This will be exploration not done. Okay, I have to check that this bar is false. Okay, if the exploration is not done, if this is true, if this is success, then I execute the exploration inside this fallback. If the exploration fails, I set this bar, and then the next time I tick the root, I don't have to execute the exploration node. I just check this condition, and because this condition not done is false, I automatically return. Okay, this is what a wart does. Wart, what it does is just wart to execute the rest of the code without having to execute any action, just checking something, a condition, something that can be in the Blackboard or something like that. Okay, then, more or less we are fine for the second part.
Professor,
tell me.
Why don't we need the always failure in the second system?
Because this always works. Then we need some way. I think that even in the slide I will show you, it looks a little bit different, but what we want is not to execute the rest. If we have been unable to set this next best viewpoint, for sure what we do not want to do is to execute the motion planner and the path follow. We don't want that. Then we need to force the sequence to fail. There are plenty of ways. Maybe you can just put here a decorator that says always fails, and then you set this in the Blackboard. This always returns success, but because you have this decorator, this fails, and it will work also. Okay, and then you can forget about the sequence. I think in the slide I have something like that. Okay. Yeah, this should be more or less, I think, for the first version, this should be more or less fine. Let me see what I put here. No, it's not showing it. Sorry, I think I have. Okay, we have a sequence. We first check in the Blackboard for this variable to be false, okay, or not true. Then we have this fallback in which we explore. Okay, yeah, it's a slightly different. Behavior 3 C++, it only assumes that we have an always success action, and then you have to this decorator that just force failure. We have probably, as I tell you, we can just put this here in the middle, and we can avoid put the force failure in the middle, and we just avoid one. Then we have the motion planner with its parameters, and then path follow. Okay, something like that. This is the basic part, okay? But this is not the full problem. The full problem is larger. Let's continue. Exploration with improved motion planning, okay? You know that when we use RRT, we have to specify a time, no? In fact, here, you see that one of the parameters in the motion planner was where I want to, the goal, that is the next best viewpoint generated by this one, by this one. The path, it's the output, but it has this timeout, okay? This timeout is how time do you want to spend looking for a solution. Then imagine that we say, okay, what we want to do is plan first with a very small timeout, 1 second, to be fast as possible. Most of the time, 1 second is more than enough to find a reasonable good path. However, if this fails, plan again with 5 seconds. Let's wait, okay? Okay, you have planned for 1 second, you have not found a path. This doesn't mean that the path do not exist. It means that you have not found it in 1 second. Let's give it 5 seconds. But what happens if still with 5 seconds it fails? Then maybe it's the situation I told you in which the robot is very close to a corner or something, and then all the paths fail, and you have to move your robot a little bit and then plan from here. Then if still no solution found, execute this separate from obstacle behavior. Let's see how we can improve this part, adding these things. Here, as you can see, is executing something. If it works, continue. If it does not work, execute something else. This is clearly a fallback, okay? Then let's change that for a fallback. And in this fallback, basically what we have is motion planner, 1 second. If this works, fine, I'm done. If not, let's do a motion planner for 5 seconds. If this works, fine. And if not, and here happens more or less the same than before. Motion planner 1 second, motion planner 2 seconds, yeah. Okay, here we can do just separate from obstacles, from OBS or obstacles, but because this normally always succeeds, what happens if this succeeds, and then we try to follow a path that we don't have, because we have no plan. Then we have to make this to fail. To make this to fail, again, we can put a decorator here, or in the example, what I put is a sequence here, the same structure that I have here, okay? Sequence, here I put separate from obstacles, and here a failure. Now what happens? Now, if we are in the last point, it fails, and because it modifies this exploration done bar in the blackboard, it will never enter again. It will just check the first conditions and do nothing else. Our execution is over. However, if it fails because it has not been able to planning with 1 second, with 5 seconds, it fails, but it has moved the robot. Before failing, it has moved the robot back. And the next time, because this is okay, this condition is fine, it will try to find another viewpoint. This is true. Probably it will give you, if not exactly the same viewpoint, almost the same, because you have almost not moved. You were here, you see some frontiers, and then you move here. Probably you will see the same frontiers. Then this next best viewpoint maybe changes a little, but maybe not. Maybe it's exactly the same. However, when you try to plan, because your robot is in a different position, probably this will succeed, and then if this succeeds, you will be able to follow the path. Okay? Then this is what I try to solve here, okay? You see it's exactly the same structure, just adding this fallback here, calling the motion planner for 1 second, calling the motion planner for 5 seconds, and then executing the separate from obstacle, ensuring that it will always fail. Only that, okay? This is all the exploration part. But here we are not checking for the look for the obstacles and grasp the object and these things. Let's see how we have implemented that. Basically, we have to do two things. First, explore and detect. It means while we move during this path following, okay, this path following action or behavior that we were executing, in parallel of this, what we have to do is check if there is any object of interest. Then we don't have to execute this path follow alone, we have to execute it in parallel with be careful, is there any object of interest around? And if some of one is discovered, then you just stop the path following, put in the blackboard the position of the object of interest that you have found, that it will be close to your local position, and then if an object of interest is detected, grasp it. Okay, then probably move towards this object, grasp the object, and put it in your tray or whatever you have, a box you have to store all the objects of interest. Okay, and we assume that the detect object will indicate the object pose. Okay, and also this object detected. Okay, it's just, if it's easy for you to have like a Boolean and a position, it can be simple. Let me just put directly the slide here because I'm running out of space. But basically, we were up to here, okay? Our previous behavior tree was till here in the middle. And now what we have had is this parallel block that instead of executing the follow path as a sequence, as this sequence of with exploration with word, no? We execute it in parallel with this detect object. And then here, our condition to finalize this parallel is that if either we reach the end path or we detect an object, if any of the two behaviors return success, the parallel returns success. Or if any of the two returns failure, the parallel returns failure. Remember that when presenting the behaviors, I told you that both path follow and detect object, we assume that never will return failure, although this is something that you could improve, okay? But now imagine that one of the two returns success, then we have to check why it has returned success. Because there is an object to grasp or because we have reached the end of the path. It can be for many of these reasons. Then here, we do this fallback. Normally, fallbacks are to replace an if condition, okay, a conditional structure. And then we say, if there is an object detected, if object detected is true, we execute the object. If there is no object detected, this fails, this sequence fails, because this is a fallback. We execute the next in the fallback that says always succeed. Then it means that this tree returns failure if the exploration is over or if we are unable to plan, okay? And it returns success if we have grasped an object or we have reached one point that we have explored, but we have not found objects in the middle. Normally, this is the behavior that you want, okay? Is that, of course, we can just say here, fail, okay? And because it fails, it returns again and starts again. But it's not nice that something that goes okay, I mean, if I reach this path here, it's because I've been able to explore, I've been able to plan a path, I've been able to follow a path, and either I have found an object or I have reached my next best viewpoint. Both things are okay. Then if both things are okay, either one or the other should finalize the whole tree in a success state, okay? I don't know why this success comes, if it comes because it has grasped an object or if it comes because it has reached the end. This is the problem of having only three possible outputs, failure, success, or running, okay? You will always have the same. But it's clear that not having more points to explore or not being able to generate a plan, this is a problem, it's a failure, and reaching the correct next best viewpoint or grasping an object, this is okay, this should be success, okay? What is clear here is that if we execute this only one, or if everything works fine, or we will reach the first next best viewpoint, or we will grasp the first object. But that's all. The tree will finish. Then here, in front of this sequence, or whatever, we will add some high-level decorator to repeat this until we detect that exploration is done, or we count how many objects we have grasped and we discover that we have grasped enough objects, whatever, okay? What you will have to do in your lab, it's almost this, but adding this extra logic at the beginning, and here adding something else, because it's not only grasping the objects, it's grasping the objects and letting them in appropriate place, okay? Then you will have to add these two extra parts, but the rest will be quite similar.